which in this case is d dt of v naught minus gt, right? So this is constant, so that's 0. And we can pull the g out, and dt is just 1, so this works out to minus g. Yeah, so the acceleration here is minus g. This, of course, is the famous constant acceleration formula that we learn in like high school physics or whatever, right? Oh, yeah? So like ignoring friction due to air, if I throw the eraser up, right? Oop, poor choice. You know, the acceleration is minus g, and here, I'll throw this less expensive chalk. Oh, yeah. Oh, yeah, I mean, so here, y naught is the initial position. V naught is initial y velocity. And g in System International is about 9.8 meters per second squared, at least on Earth. That's the gravity, right? Yeah, like, for example, right, if I have this chalk, it's a meter up, right, and I throw it, then I gave it some initial velocity as it leaves my hand, v naught, and the formula it follows as a function of time is y naught plus v naught t minus 1/2 gt squared. If v naught's 0, then this happens. So, but yeah. This equation doesn't account for my hand holding the chalk, and it doesn't account for the floor stopping it, right? It just doesn't know about that. Anyway, so physics, you know, we can talk about position, velocity, acceleration. That's a nice application. And another application, so this application, so this was motion in one dimension. Another application is graphing. And this is an ongoing application in here, but graphing is vastly improved with the help of calculus, all right? So, for example, we can go back to my example 1 over there, and we can pick on it some more, like graph y equal to x squared plus 3x to the 4th. I can ask a question. I mean, first, so that function is sufficiently simple. You can tell me the x-intercepts for it, right? What are they? So I'm going to call this f of x, right? So I'm going to put the graph up here to keep it out of my way. But, you know, with algebra, you can see what we have here is x squared times 1 plus 3x squared, right? Which I can tell you bounces off here, right? It's got an x-intercept of 0, and that's it. I'm not sure exactly what happens over there, but I mean, with algebra, that's about all I could do, besides plugging in some points, right? But I can do a little bit better now. I can find the tangent line. Through, say, a comma f of a. What would that be? So f of a is a squared plus 3a to the 4th, right, for this function. what's the derivative? What's f prime of a? See, I take my 2x plus 12x, what was it, cubed. I take that formula, and I set x equals to a in that. That gives me the slope of the tangent line at that point. So this is at 2a plus 12a cubed. So the equation of the tangent line would be, y equal to f of a plus f prime of a times x minus a by definition. But for this particular function, we can plug it in. What is that? That's a squared plus 3a to the fourth, parentheses 2a plus 12a cubed times x minus a. So there you go. That is a formula that would allow you to graph the tangent line to this function at any point. But I think perhaps the most interesting question to ask is, are there any points in this graph where the derivative is 0, because that would be a place where you might have a horizontal, tangent line. Like, is there something I'm missing? Is there out here, is there somewhere where it does like this? Does it have one of those? What do you think? I don't know right offhand. But I can figure it out, because if there was a place like that, there would be what? These would be places where f prime of a was equal to 0. See, so I can look for turning points in the graph by looking for places where the derivative is 0. Is the derivative 0 for this graph anywhere? I think it's 0 at one point. Yeah? At here? Yeah, I think that's going to be the case, but let's work it out, right? Here's the derivative. Set that equal to 0. What do you get? We get 2a times 1 plus 6a squared, right? So this either gives a equals to 0. This is the only point with f prime of a equals to 0. So what that shows me is, in fact, this right here could not happen for this given function. In fact, it's as boring as we thought it was with algebra to start with. It just looks something like, roughly speaking. Now, it turns out later in the course we can do better by also looking at the second derivative. We can look for what are called inflection points, but we're not quite there yet. But just looking ahead. So to find a turning point in a function, what do we need to do? What are we looking for if we're looking for a turning point in the graph of a function? We're looking for a place where the derivative of the function is what? Is 0. So this wasn't especially exciting because the turning point is, right there. Anyway, I think that's a pretty good place to stop for today. So when was your homework? Mission 4 due? The 8th? Is that Monday? Okay, good. The only thing I have yet to cover here in that list of topics that I see is the exponential. So I should talk to you about the derivative of the exponential probably next time we have lecture. In short, the answer is just this. I mean, d dx of e to the x is e to the x. That's kind of it. But anyway, I'll stop here.